All right, mon amis, it's time for us to do some practice with problems involving L'Hôpital. Now, it's important that you do practice because even though L'Hôpital problems sound fun and easy, because they are fun, they're not always easy. There's sometimes a little bit of subtlety, so that's why we need to do practice. And it's important that you do as much practice on your own as you can. So if you're following along with the video, please make frequent use of that pause button so that you can say, okay, I wonder what I would do next. Let me try something, and then do it. And then once you're done, we can compare answers. And hopefully, we got the same answer. Well, I think we'll do pretty well. All right, well, let's begin. So, our first problem. Find the limit as theta goes to 0 of 3 theta minus sine theta over theta. Now, this is a problem that we actually don't need to do L'Hôpital to get the answer for, because we have other ways to do this problem. For instance, we could say that this expression here is the same as 3 theta over theta, which is 3, minus sine theta over theta. And we know that, hey, look, sine theta over theta, that's a famous limit. We spent a lot of time talking about that one. We know that as theta goes to 0, sine theta over theta goes to 1. So this is going to 1, which means our answer goes to 3 minus 1, which is 2. All right, so now we know what the answer is. Let's just see what L'Hôpital tells us the answer should be. Now, before you ever apply L'Hôpital, remember first, you have to see, is it valid? Now, there's really a couple of conditions, but the main condition to check is it going to the proper indeterminate form? So if we have our limit here, we have our theta going to 0 of 3 theta minus sine theta over theta. We ask ourselves the question, what's going to happen upstairs? We'll plug in 0. 3 times 0 minus sine of 0. Well, that's 0. Plug in 0 downstairs. Well, that one's really easy. 0. 0 over 0 means it's an indeterminate form, which we can apply L'Hôpital. All right, good. So next step is apply L'Hôpital. So I'm going to put a little mark here, LH, indicating this is where I'm using L'Hôpital, and that's the justification for the equality, assuming that we get an answer at the end. If we didn't get an answer at the end, then everything breaks down and we have to try something else. For example, circling our answer up here. That's a really nice alternative, is to circle the answer. All right, so remember, not a quotient rule. So the derivative of the top, 3 theta minus sine theta. Derivative of that, well, it would be 3 minus cosine theta, because derivative of derivative of sine is cosine. Derivative of the downstairs, well, derivative of theta with respect to theta is 1. Okay, well, what does this go to? Well, notice the denominator is not going to 0, which means game over. Whatever happens, it happens right now. So, all right, good news for us. So, it's going to go to something over 1. Well, what's upstairs? 3 minus cosine 0. Well, cosine of 0 is 1. 3 minus 1 over 1, also known as 2. And good. Hey, they match. Well, of course they match. If we got different answers, then that means that we did something wrong on one of the two processes, because the answer will always be consistent regardless of which way you go about answering the question. And of course, we're getting to the parts of math where you may have different ways to answer a question. That doesn't mean math is more challenging. It means math is more fun. A lot more fun. All right. Well, one down. Let's do another problem. All right. So our next problem. Find the limit as t goes to 0 of sine of 5t over e to the 2t minus 1. Okay, now this one, maybe it's not so obvious what to do as the last one was, where we said, hey, we can use our old tools. This one's a little bit more dicey. I don't know if we'd be able to do it quite so cleanly here. So let's think about things that we could do here. All right, well, we suspect L'Hôpital. Well, why do we suspect L'Hôpital? Well, because, that's what we're talking about today. But let's think about the other thing. Of course, if you're dealing with any limit, a good rule of thumb is to say, well, what happens if we plug it in? In other words, what's happening at 0? So let's check that out. So we have the limit as t goes to 0 of sine of 5t. Divide that by e to the power 2t minus 1. And when we plug in 0, you get sine of 0 over e to the 0 minus 1. But of course, sine of 0 is 0. E to the 0 is 1. 1 minus 1 is 0, which means we have 0 over 0. And as I like to say, 0 over 0 means more work, more work. All right, so we need to do some more work. And what's our more work? Well, we have the right kind of form. It's a fraction, 0 over 0, so we can apply l'hôpital. Ah, l'hôpital, mon ami. Oh. I tend to do that a little bit, you might notice. The oh. You don't have to make the noise to apply the rule, by the way. It's just some fun. And shouldn't math be fun? All right, don't forget, we need to keep writing the limit down because we're still taking our limit. So the derivative of sine of 5t, we need to apply the chain rule here. So the derivative of sine would be cosine. And then take the derivative of the inside, we put a 5 in front. So 5 cosine of 5t. Derivative of e to the 2t, again, would be a chain rule, 2 e to the 2t. And then derivative of minus 1 is 0. So that goes away. All right, now we can kind of see, hey, the denominator is looking pretty good. It's not going to 0. All right, so what does it do? Well, we get 2 times e to the 0. And e to the 0 is 1, which means that the denominator is not 0. It's game over. Whatever happens, it's happening right now. All right, well, how about the numerator? Well, it's 5 times cosine of 0. All right, so, well, cosine of 0 is 1, e to 0 is 1, so you end up with 5 halves. And that's the answer. Notice, see, 0 over 0, a lot of people say, it's just 1, right? No. In some cases, it's 1. In other cases, it might be 5 halves. In other cases, it could be something else. It's why we have to do the work. You have to do the work. It's why we call it indeterminate. We don't know. Yeah, but we can find out. And isn't that great that we can find out stuff? It's wonderful. Wonderful. All right, well, let's do another problem. Of course. So our next problem. Find the limit as t goes to 0 of cosine of 3t minus 1 minus t squared. Divide that by e to the t plus e to the minus t minus 2. All right. Well, let's think about it. Okay, so this is limit as t goes to 0. So we have upstairs cosine of 3t minus 1 minus t squared. Downstairs, e to the t plus e to the minus t and minus 2. Now, what do we check? Well, plug in 0. We should always plug in our point and see what we get. Maybe we don't even have to do anything. I suspect we might have to do something on these problems, but you should always check. Okay, so what is this going to? Well, e to the 0. That's 1. E to the minus 0 is still 1. And minus 2. Got 0 downstairs. I suspect something's going to happen upstairs. Okay, cosine of 0 is 1 minus 1 minus 0 squared, 0. All right, so what do we have? Well, 1 minus 1 minus 0 is 0. 1 plus 1 minus 2 is also 0. 0 over 0, indeterminate. Okay, which means more work, more work. All right, well, in particular, in this case, it means let's apply l'hôpital. Let's see what we get. So, doing l'hôpital, again, you should mark what you're doing. I like to do it with a little LH, but you can say apply l'hôpital, whatever you need to do. All right, so this is going to be a limit as t goes to 0. So upstairs, chain rule, root of cosine is negative sine, so you're going to get negative 3 sine of 3t. And that 3 here comes from the chain rule, right? Because take the root of the inside would be 3. Root of minus 1 is 0, and then you get minus 2t. Downstairs, we're going to get root of e to the t, e to the t. Root of e to the minus t is minus e to the minus t. Again, that's a chain rule, because take the root of minus t is a minus 1. That's where that minus sign is coming from. And the root of minus 2 is 0, so that goes away. Now, oftentimes we can kind of mentally do a quick check and say, what's happening? And we see, looks like things are not done yet. So e to the 0, and this will be e to the 0, and you're subtracting. So let's see what it's going to. So this is going to downstairs, it's going to 1 minus 1, because e to the 0 minus e to the 0. Upstairs, you get minus 3 times sine of 0. Well, that's 0. And then minus 2 times 0. Well, those are both 0. So you get 0 over 0. Which means more work. Yes, exactly. We're going to keep going. And we're going to keep going with L'Hopital because we say, hey, it's simplifying, right? You know, we got rid of a term downstairs. We got rid of a term upstairs. There is a hope. There is a hope. So we keep going. Okay, so apply L'Hopital again. And we get the limit as t goes to 0. All right, the derivative of negative 3 sine 3t. Well, derivative of sine, cosine. Then we remember the chain rule. So there's going to be a 3 that comes out. So that will be minus 9 cosine 3t. And then minus 2, because take the derivative of minus 2t. All of that, divide that by downstairs. Derivative of e to the t is e to the t. And then minus a minus e to the minus t, which is plus in e to the minus t. And now we sort of scan and say, looks like things aren't going to be canceling. So it looks like we're going to be done. So what does this do? Well, downstairs, e to the 0 plus e to the 0, 1 plus 1. See, now that's not a 0 downstairs, so it means definitely game over, game over. How about upstairs? Well, you get minus 9 times cosine of 0, so that's minus 9, because cosine of 0 is 1, then minus 2. And so we end up with negative 11 halves. And that's our answer. There you go. Good. And you see, really when you apply L'Hopital, you need a couple of things. It has to be differentiable, and we can see that these are nice functions. It's differentiable. Has to go to some indeterminate form, which is what we've been doing when we checked, 0 over 0. And the other thing is you have to get an answer at the end. See, these equals are only true once we know for sure that we have an answer at the end. And since we did, then we got the right value. And that's our answer. These are great. Wow, we should have started with L'Hopital, right? Well, a lot of people feel that way. But the thing is, we can't start with L'Hopital until we have the rules for derivatives in place. And we need to figure out what the rules for derivatives are. So that otherwise we get sort of trapped in this vicious circle. So we had to wait. So this is the right time for us to start talking about L'Hopital. We didn't wait because we didn't love you. Of course we love you. You're our best student. We waited because we had to do it at the right time. All right. Well, let's try another problem. Okay. Find the limit as t goes to infinity. Ooh, a little different. Now it's going towards infinity. Of t to the power 314. Divide that by e to the t. All right. Wow, that's huge. Just think about it. So, for example, if you put in t equals 2, 2 to the 314 is a ginormous number. Ginormous is a technical term for really big. It's huge. It's huge. We're talking like atoms on the universe kind of scale number. On the other hand, e squared, it's a little less than 10. So, absolutely gigantic number underneath 10. Plug in 3 to the 314. Like, wow, now we have to go into multiple universes. And e cubed, I don't know, 30, definitely under 30. Like, what? So what's happening? This is gigantic. This is big, but not that big. So, what's happening? Well, let's think about it. Let's figure it out. Now, in the long run, of course, as you head to infinity, we're just getting big number over big number. So, what we can say to start is that really this is initially heading to big over big. All right, now that's one of our indeterminate forms, which means that we can apply L'Hopital. All right, so let's apply L'Hopital. So we'll do it once. So here we go, L'Hopital. This becomes a limit as t goes to infinity. Through the top, the 314 comes down, then it's t to one less number, 313, over e to the t. Okay. Now, what happens to this? Well, it's going to infinity over infinity, right? Because e to a big number is big, and a big number to a power is big. Okay, so, what do? Well, we apply L'Hopital again. L'Hopital. And we just see what we have. So that'll be 314 times 313 times t to the 312. Divide that by e to the t, right? What does that do? Well, that goes to infinity over infinity, right? Because it's a big number. Downstairs, e to a big number is a big number. And a big number to a power is big. Okay, so what do? Well, we keep going, right? Now, we'll apply it one more time, right? Limit as t goes to infinity of 314 times 313 times 312 times t to the 311 over e to the t. And still going to big over big. And it doesn't really feel like much is changing, right? Because we still say, hey, it's still going to big over big, and we do it again, it's still going to big over big. Is this a case where we're just sort of like, give up? The answer is no, because notice that things are getting better. Now, how are things getting better, you say? Look at our exponent. See, we started all the way at the beginning, 314, then we said, hey, it's 313, and then 312, and then 311. See, they're slowly working its way down. And in fact, this is one of these beautiful times in math when we can say, aha, I see a pattern. Now, this is going to be ... and of course, ... this is just code for whenever you see a ... means the pattern continues. And so what we'll do is we'd say, look, we're going to keep taking L'Hopital's rule. Every time we take a L'Hopital rule, the exponent upstairs goes down by 1. The downstairs never changes. And so we repeat that until something interesting happens. Well, as long as you have t to a power, you're going to keep getting a big number. So if we apply L'Hopital's rule, a grand total of 314 times. Okay, so we're not going to write them all down. That's the advantage of the ... Saves us a little bit of time. So after we've applied L'Hopital's rule many times, we come to the conclusion that this is the limit as t goes to infinity of 314 times 313 times all the way down to 2 times 1 and no power of t. See, we've knocked the power of the t all the way down. Eventually, at the 313th time, it's just t to the 1, and then the next time it was 1, constant. The downstairs is e to the t. Now, what happens? This is important. The numerator is a gigantic number. It's a ridiculously big number. It's a number that you would never want to encounter. It's just so big. It cannot be easily contained. But, and this is important, it's a big number, but a finite number. So, in fact, there's a shorthand notation. This is going to 314 factorial. That's what that exclamation mark. It doesn't mean it's like 314. Ah! No, it means 314 factorial. Downstairs, it's infinity. So it's a fixed value on the top, something getting bigger and bigger downstairs. And so what it really means is that it's going to 0. And that's the answer. Now, the moral of this lesson for this particular rule here is, look, whenever I have t to any power, I can keep applying L'Hopital's rule and eventually knock the power down to either something where it's constant if it's t to a whole number, or even something where it's negative. Whereas when I take derivatives of an exponential, it still looks like exponential. So what this really means is you can say, hey, look, polynomials are really very small compared to exponentials. So exponentials grow much larger than polynomials. So oftentimes we talk about rate of growth, and we like to say, hey, look, polynomial growth, yeah, that's pretty big. But exponential growth, like, wow, that's really big. That's really big. And this is the justification that lets us say things of this nature. Ah, what a good problem. Great problem. Okay, well, let's try another problem. Of course. We should try lots of problems. All right. Find the value a so that the function g of x is continuous at x equals 0, where our function looks like e to the 3x minus e to the 2x minus x. Divide that by x squared if x is not 0, and a if x equals 0. And it says justify your answers using limits. Now, what are we trying to do? Well, whenever we want something to be continuous, what needs to be true is that what happens at the point, in particular, here our point is 0. So what happens at 0 is what we think should happen at 0. So what happens at 0? Well, the answer is we get this value a. So we have that a is the value of the function at 0. In order to be continuous, the value of the function at 0 has to match what we think the value of the function should be at 0. So the limit as x goes to 0 of g of x. All right, so far so good. Well, now what? Okay, well, what's the limit? Well, we know we are not at 0, right? Because when x is going to 0, we're not 0. So what can we do? Well, the answer is what we can do is we can use now this form. So this is really the limit as x goes to 0 of e to the 3x minus e to the 2x minus x. Divide that by x squared. All right, so our problem has really become, aha, find that limit. But we phrased it in terms of continuity to sort of mask a little bit what we were looking for. But we could see through this facade. We know what we're really after. What's our limit? Well, what do? We do what we always do. We say, well, plug in 0. And we see downstairs, 0 squared. That's sort of a sign we might have a little bit of work ahead for us. 0 squared is 0. E to the 0, 1. E to the 0, still 1. And then 0 is 0. Okay, so we're going to 0 over 0, which means, of course, more work. All right, and our more work is l'hôpital, l'hôpital, mon ami. All right, so applying l'hôpital. Still have the limit, hasn't gone away yet. Take the derivative of the top, derivative of e to the 3x, using the chain rule, 3e to the 3x. Derivative of e to the 2x will be 2e to the 2x, and the derivative of minus x minus 1. Derivative downstairs, derivative of x squared, 2x. Well, I'm suspicious because I know we're plugging in 0. I see 2x, 2 times 0 is 0. So, I'm thinking the downstairs is going to 0. How about the upstairs? Well, 3, because e to 0 is 1. So 3 minus 2 minus 1. That's 0. So it says 0 over 0 yet again. Well, what does that mean? It means more work. Okay, well, that probably won't surprise us. Okay, so what's our more work? Well, l'hôpital. Okay, so we're going to apply l'hôpital again. So this will become our limit as x goes to 0. Okay, upstairs, 3 comes down again, 9 e to the 3x. 2 comes down again, 4 e to the 2x. Minus 1, derivative of that is 0. Downstairs, the derivative of 2x is 2. And now we see, aha, game over. Because the denominator is definitely not 0, which means we're going to get a limit. And so, aha, whatever the answer is, it's going to happen right now. Okay, so what do we have? So upstairs, In fact, we don't even have to say goes to. We can say equals, because we can just plug in 0. These are nice functions. 2, 9e to the 0 is 9. 4e to the 0 is 4, because e to the 0 is always 1. So 9 minus 4 over 2, also known as 5 halves. And there you go. That's it. That's the answer. Goes to 5 halves. Good. Nice. Fun problem. Fun problem. All right, let's do another problem. Woo! Okay. Find the limit as x goes to infinity of x plus sine of x all over x. All right, well, this looks like a fun problem. So let's try it out. So what do we have? Well, the first thing we should think about is, well, what's happening to x plus sine x and what's happening to x? Now, it's easy to say what's happening to x. X is going to infinity, so the denominator is going to infinity. That makes us think we might have a L'Hopital in our future, right? Well, let's look at the numerator. Okay, so this is infinity, but what's happening to sine of x? Well, the answer is that sine is sinusoidal. In other words, it's just going up and down. It's oscillating between -1 and +1. It's small, and therefore, in the long run, the sine of x is contributing very little to what the value should be. Okay, so that says that, well, x is getting big, sine of x doesn't get big, and therefore, on a whole, it's heading towards infinity. All right, good. All right, so infinity over infinity. So what do? It's indeterminate. So we apply L'Hopital. L'Hopital. Okay, so applying L'Hopital, we get that this is the limit as x goes to infinity. Well, derivative of x plus sine of x, that would be 1 plus cosine of x, and then downstairs derivative of x is 1. All right. Well, this is great. We're almost done. And certainly we're not going to anything 0 or infinity downstairs, so it should be game over, right? Okay, let's think about 1 plus cosine of x. And what do we know about cosine? Well, it's like sine. It's this going up and down, up and down. It goes between +1 and -1. And now, what happens to it as we head off to infinity? Well, the answer is it really just keeps going up and down, up and down, up and down. So it's not heading towards any particular value. So what's the answer? Well, the answer is that this limit here, it does not exist. Now, let's pause. What does that say about our original limit? Now, you might say, aha, so our original limit does not exist as well, right? Right? Well, no. Here is the problem. Remember that one of the things we said about L'Hopital's rule is that when we apply it, there's a couple things that have to happen. It has to be differentiable, has to go to something indeterminate, and that the resulting limit that you come up with has to exist. Since this limit didn't exist, what that means is that when you apply L'Hopital, it actually fails. So you can't apply L'Hopital. All right, so we've got to throw L'Hopital out. And now we're just sort of like, what can we do? What can we do? Okay, so, well, we know what we can't do. We can't apply L'Hopital. But we don't want to give up hope. We're optimists. We think we can probably figure something out. So let's take a closer look at the limit that we have here. So let's look at it again. So x plus sine of x over x. So we can rewrite this limit by breaking it into parts. So in other words, I can think of it as x over x plus sine of x over x. Now x over x, it turns out, true story, it's 1. I swear, it really is. So that's easy to figure out. Now, how about sine of x over x? Now you might be thinking, sine x over x, right? We know that limit. Well, be careful. We oftentimes talk about sine x over x as x is heading towards 0. What's happening as it heads towards infinity? Well, we say it's a story of two parts. You have the downstairs part, which is the x, and this is getting big. Then you have the upstairs part with the sine of x, which is something which doesn't get big. It actually stays bounded. It's between +1 and -1. So if I have something which is not getting very big, it's going between +1 and -1, divided by something which is getting huge, what's the result? Well, the result is it's going to get smaller and smaller and smaller. So this part, sine x over x, as we head towards infinity, goes to 0. And therefore, the answer to our original question, what is this limit of x plus sine x over x, is it goes to 1. All right, so be careful. Remember, if you don't get a definite answer at the end of L'Hopital, that means you can't apply L'Hopital, and so you have to look for some other method. Or you check your work. I would probably check your work first, because it's likely we made a mistake at some point if we didn't get a good answer. But here, it was so simple that we did it right. Okay, good. Well, let's try some more problems, right? All right, another problem. So, find the limit as y goes to 0 from above of y times log of y. Okay, so the nice thing is, the fact that we're going from 0 to above means we're always plugging in a positive number, which is good because we have a log involved. We never want to plug a negative number into a log, because that's bad. You can't do it. You can't do it, at least not in our class. Maybe in a different class you could do it, but not in our class. Okay, now, can we apply L'Hopital, and why not? Well, the answer is we can't apply L'Hopital yet. And the reason we can't do it here is because it's not of the right form. You see, this limit here is indeterminate. So if you look at what this limit is doing, there's really two pieces here. There's the y and the log of y. The y part is getting close to 0, and the log of y, well, if you're familiar with the log function, what does it look like? It looks something like this. So that as you're approaching 0, the log of y is heading towards this asymptote. So this is heading towards a minus infinity, which is really think of it as a big number. Okay, so you got 0 times big number. So this is going to something indeterminate. All right, so, which wins out? Well, we can't say. We don't know. So we got to do some work. And in order to do our L'Hopital, we have to get it to a fraction. So now we have a choice. We have to get it into something over something, which means that one of these two pieces has to somehow end up downstairs. So how do we get it downstairs? Well, we can do one of two things. We can say, look, let's move the y downstairs. And if we did that, what would it look like? Well, to move the y downstairs, I'd just turn it over as I move down. So as it moves downstairs, you flip something over. So you'd have the log of y staying upstairs, and this would become a 1 over y. Of course, if you can move the y downstairs, you could also move the log of y downstairs. So what would that look like? Well, the y stays put, and then you have 1 over log of y. These are both valid things that you can do. And they might say, well, which one do we want to do? And the answer is maybe not so obvious at the start. But the good rule of thumb to remember is let's do the one which will make things easier in the long run. Okay, so let's work through the derivatives. And I think when you see the derivatives, you'll say, aha, I think I see which one we should stick with. So we can apply the L'Hopital's rule because you'll notice here, this is going to 0 over 0 because you have 1 over a big number is 0. Here it's an infinity. 1 over 0 is like infinity. So it's infinity over infinity here, 0 over 0 here. Don't be swayed by, oh, 0 over 0 sounds better than infinity over infinity. No. Don't think that way. All right, so if we apply L'Hopital's rule here, what would we get? Well, we'd have a limit as y goes to 0 of what? Well, 1, right there at the top. Now, how do you take the derivative of 1 over log of y? Well, the answer is, you really think of this as log of y to the minus 1. And so the minus 1 comes down, and you have log of y to the minus 2, then times that by the derivative of log of y, which is 1 over y, chain rule. Okay, so what do you end up with? So this is the limit as y goes to 0 from above. You have a minus 1 over y log of y squared. Or you could also say this is the limit as y goes to 0 from above of minus y times log of y quantity squared. All right, well, do you notice? This looks even more complicated than what we began with. See, our rule of thumb is let's make things less complicated. If we make things less complicated, there's a chance that we might be able to actually solve it. And that's our goal, right? We want to solve all the problems. All the problems. We're a little bit suspicious here. Things got worse, not better. Okay, well, let's look at the other route and see maybe something nice happens there. Okay, so again, similar process. So we're going to apply L'Hopital here. And we'll again think of 1 over y as y to negative 1. So this is the limit as y goes to 0 from above of, well, upstairs derivative of log of y is 1 over y. Downstairs, derivative of 1 over y, well, the minus 1 comes down, and then it's y to the minus 2. Okay, well, what does that look like? Well, this y to the minus 2, it's really like a 1 over y squared, and then I could flip it upstairs, and what do we have? Well, if you clean it up, you get this is the limit as y goes to 0 from above of minus, coming from that minus right there, y. Now, what do you notice? Here, the expression, it's simpler. So, we're going to go with this route. In fact, now we can receive the answer. We say, aha, it's 0. Because y is going to 0, so minus y goes to 0. And there we go. So, that's the answer. So the moral here is sometimes you might have a choice into what form you want. And generally speaking, you try to think of what would be the easiest thing to take a derivative of. 1 over log y versus 1 over y. 1 over y sounds something that's a lot easier to take a derivative of because you'll end up with something that more or less looks the same. Whereas 1 over log y tends to get more complicated. So when you're thinking about how to modify your form to get it into something usable, think to yourself, what would make it easier for me in the long run? Because I like myself. I value myself. And I want to make sure I give myself the best chance to succeed. Good problem. All right. Well, let's try another problem. Aha! This one should be good. This one should be really good. All right. Find the limit as z goes to infinity of the square root of z squared plus 4z minus z. Okay. Now, before we start, let's ask ourselves the question, what's happening here? Well, we see this is getting big, and this is getting big. So what's happening is we're getting something like infinity minus infinity. All right, infinity minus infinity means indeterminate. Okay, so we don't know what it is. Well, but maybe we can figure it out if we could get to L'Hopital. So we want to turn it from a subtraction into somehow a division. So how can you turn subtraction into division? Well, there's no fractions to begin with, so we're going to introduce a fraction. And then we'll say, well, while we're at it, let's do something with the square root. So, and our idea is we're not going to do L'Hopital yet, but we're going to use the conjugate. So the conjugate is a way to help get rid of square roots, and in the process of doing the conjugation, we'll end up with introducing a fraction. So remember, the conjugate means that we're just going to change the sign in the middle. So instead of a minus e on the end, it's a plus c. So there we go. All right. So multiply top and bottom by the conjugate. Good. Now, the square root, we'll get rid of them. Because remember, it's really a minus b times a plus b, so it ends up being a squared minus b squared. So you get rid of the square root, and so you're going to get z squared plus 4z, and then minus z squared. Ah, that's fantastic. So this becomes the limit as z goes to infinity of just 4z. Beautiful. Downstairs, what do you have? The square root of z squared plus 4z plus z. Okay, now, there you go. Okay, so what does this do? Well, z is getting big, and so this part's getting big, that part's getting big, and also the square root of z squared is getting big. So all our pieces are getting big, and notice this is being added here, which means this is going to a huge number over a huge number. Now we can apply L'Hopital. We put it into the form where L'Hopital can be applied. Okay, so we apply L'Hopital. So here we go, L'Hopital. So this becomes our limit as z goes to infinity of what? Well, derivative of 4z, that's easy, that's 4, over the square root of z squared plus 4z. Now, as a reminder, what is another way to think of the square root of z squared plus 4z? That's really z squared plus 4z to the 1/2 power. All right? So when we take our derivative of that, what will we have? Well, we'll have a 1/2 comes down, z squared plus 4z to the 1/2 minus 1, which is minus 1/2, and then we'll have a plus 1. Ah, whoops. What did I forget? You see? Ha ha ha. Not yet, not the plus 1. I forgot the chain rule. So I have to multiply by the derivative of z squared plus 4z. So this is really a big dot for multiplication, really big dot. So that's times 2z plus 4, whoops, and then the derivative of plus z is plus 1. Okay, all right. So let's clean that up. So what do we have? So this is our limit as z goes to infinity. Well, the 1/2 multiplies by the 2z plus 4 fairly nicely. So we get 4, and then we have a z plus 2 over the square root of z squared plus 4z, and then plus 1. All right, well, let's get rid of our fractions within fractions. Multiply top and bottom by square root of z squared plus 4z. So this becomes our limit as z goes to infinity of upstairs 4, the square root z squared plus 4z, and then downstairs we have z plus 2 plus the square root of z squared plus 4z. Okay, good. Now, what's happening here? Okay, well, what's happening is you get a big number, and then big number plus 2, plus 2 doesn't really do anything, plus a big number. So this is going to infinity over infinity, right? So what do? Well, you do what you almost always do when you see something that looks like infinity over infinity, which is you apply L'Hopital. All right, so we're going to apply L'Hopital. And what do we get? Well, upstairs, we're going to have the following. So don't forget, we still have our limit coming all the way along. We always write our limit down until we're done with our limit. So we'll have 4, and the derivative of the square root of z squared plus 4z, well, we actually did it over here. See, it's the 1/2, then the z squared plus 4z to the minus 1/2 times 2z plus 4. So it becomes z plus 2 over the square root of z squared plus 4z. That's what that part becomes. It's right there, right there. All right, divide that by, downstairs, 1 plus z plus 2 over the square root of z squared plus 4z. Okay, let's get rid of our fractions. Okay, so if we get rid of our fractions, multiply by the square root of z squared plus 4z, well, what do we end up with? Well, we end up with a limit as z goes to infinity of, upstairs we have 4 times z plus 2, and then downstairs we have the square root of z squared plus 4z plus z plus 2. Well, what is that going to? Aha, no big surprise. Infinity over infinity. Okay, so what do we do? Well, you're probably thinking, well, let's just keep going, right? Because you're like, I'm going to keep going all the way. And we're going to keep going. But I hope you start having the sort of like, oh, something's not right here. We're in trouble. Because something's not right here. We're in trouble. Okay, but we keep going. Don't worry. We will get an answer at the end. Somehow. Okay, so we're going to proceed with, again, a L'Hopital. So take the derivative of the top. Well, the derivative of 4 times z plus 2 would be what? Well, it's 4. So this is the limit as z goes to infinity of 4. Then the derivative of the square root of z squared plus 4z, well, we've done that before. That's z plus 2 over the square root of z squared plus 4z. And then the derivative of plus z plus 2 is plus 1. Now, here, we're going to pause for a second and say, have we seen anything like that before? And of course, when we ask a question like that, you know that the answer is we must have. If we look here, they're the same, which means that we're now in sort of this cycle. We could simplify this, then apply L'Hopital again, and then simplify it, and then apply L'Hopital again, and keep going in circles. Applying the L'Hopital is not helping us get things simpler and simpler. And therefore, it's not going to help us get to our answer. So this is a case when we're kind of getting stuck when we think about applying L'Hopital, which means it's probably not the right way to go. But remember, we were doing limits before we did L'Hopital, which means there's probably a way to do this without L'Hopital, because there's a way to do this without L'Hopital. But what's the way? So we're going to come back quite a way. So let's forget this part right here. And let's start here. Suppose we didn't know what L'Hopital was, and we were doing this problem from an earlier part of the course. We said, well, what's happening? We've got things which are getting big. So what do we need to do? We need to slow things down. Pump the brakes, slow it down. Well, how do you slow it down? You say, well, what's causing it to get big? The answer is this z is the thing that's driving the growth upstairs. So the upstairs grows like z. So we say, well, let's slow it down by that amount. So using our old ideas, we'd say, well, let's multiply top and bottom by 1 over z. Now, if I do it by multiplying top and bottom by 1 over z, it's equivalent to multiplying by 1. Okay, so this becomes our limit as z goes to infinity. And upstairs, 4 times z times 1 over z is 4. Then z times 1 over z is 1. And now, this 1 over z, I can move it into a square root. And because z is going to positive infinity, I can replace z by really the square root of z squared. So I can move it into the square root and simplify. And I'll let you work out the details. But at this point, I hope you can do it. If you're stuck, let me know, and we'll walk through it. So z squared over z squared, because remember, that's going to go as a z squared into the square root, is 1. 4z over z squared is 4 over z. So what do we have? Well, the only place that z now shows up is right here. And it's as a 4 over z. 4 over z is going to get small, tiny, go to 0. So what do we end up with? Upstairs it's going to 4. Then the square root of 1 plus 0 is 1 plus 1. And therefore our limit is 2. And that's the answer. I told you we'd do it, and we did. But this is a case where we didn't have to use L'Hopital. And in fact, applying L'Hopital would get us into this vicious circle. So remember, the old ways are still good, and sometimes even better. So don't forget, don't discard old ideas. There's value to them. All right. Time for another problem. Okay. So, given that f of x is twice differentiable, which is just another way of saying we can take two derivatives, find the limit as h goes to 0 of f of x plus h minus 2f of x plus f of x minus h all over h squared. Okay, now this is good. In fact, there's a wonderful story to this, and we'll get to it in just a moment. First question is, does L'Hopital apply? Because, we're doing L'Hopital. So does L'Hopital apply here? So let's think about it. So the first thing is, let's plug in h equals 0. And I will say one of the hardest parts about this particular problem that we're going to do is notice that we have two things that look like variable names, x and h. See, we oftentimes think of x as the variable name, but what's the one that we want to think of as being the variable? What's the part that's changing? It's the h. You see, because h is going to 0, which means that the h is changing. So don't get caught up on the fact that you see an x there. It's the h that changes. Okay, so when we plug in h equals 0, what do we get? Well, so we'll just do a quick computation here. You get f of x minus 2f of x, and here a plus f of x. All right, and then downstairs you get 0. Well, this is f of x minus 2f of x plus f of x is 0 over 0, which means more work, more work. That's all right. We don't mind doing more work because we like to know the answer. Okay, so 0 over 0 means, of course, L'Hopital. Ah, L'Hopital, mon ami. Good times. So we're going to apply L'Hopital. And what do we get? Well, this is the limit as h goes to 0. And remember, we're taking the derivative, we're thinking of h as our variable. So what's the derivative of f of x plus h? Do the chain rule. You'd have f prime of x plus h, and then times the derivative of the inside. Well, the derivative of x plus h would be 1, because the derivative of x is 0, derivative of h is 1. All right, derivative of minus 2f of x is 0. 0, because there's no h at all. It's not changing with h because h is not involved. Be careful. Okay, how about this one? F of x minus h. Well, it'd be the derivative of the outside, f prime of x minus h, times the derivative of the inside, derivative of x minus h would be negative 1. Derivative of x is 1, derivative of minus h is minus 1. So it really becomes a minus f prime of x minus h. Now, all of that is divided by derivative of h squared is 2h. Okay, so what does that go to? Well, it goes to f prime of x minus f prime of x all over 0, also known as 0 over 0. Which means more work, more work. But that's okay. We don't mind. We do what? Well, we apply L'Hopital. L'Hopital, of course. So this is going to be what? The limit as h goes to 0. All right, taking the derivative here. Again, chain rule, f double prime of x plus h times 1. By the derivative of x plus h is 1. Then here, minus f prime, f double prime, because we're taking the derivative of the derivative, so f double prime, two derivatives, and then x minus h times the derivative of x minus h, which is a minus 1, which turns the minus into a plus, divided by derivative of 2h is 2. And now we know game over, because the denominator is not going to be 0. It's going to be 2. So this goes to what? Well, 2 downstairs. Here we're going to get f double prime of x. And then we're going to get again an f double prime of x. And that makes 2 f double primes of x's over 2. And therefore, the answer is f double prime of x. And there you go. All right. Now, why is this interesting? Well, it turns out that suppose you're trying to estimate the second derivative of some data, and all you have is a bunch of data. You don't have the original function. How do you go about doing it? And the answer is you do something along the lines of the following. You say, look, you look at some samples of the points. You say, well, look, I have the value of the function here and the value of the function on either side spread out evenly. And you say, well, if you weigh it, f of x plus h minus 2f of x plus f of x minus h all over h squared, that's actually a reasonable approximation to the second derivative. So computationally, this is actually a tool that can be used when we're trying to get some estimates, numerically at least, for the second derivative. So a nice application. Who knew? Well, maybe L'Hopital? No. He did this, of course, long before they had computers. But it's nice to see things getting used. It's good to know things have nice uses. All right, well, let's do another problem. All right, given that f of x is a twice differentiable function, and the limit as x approaches 2 of x times f of x plus 4 divided by x minus 2 squared is equal to 3, well, find f of 2, f prime of 2, and f double prime of 2. All right, well, that's interesting. You see, because normally when we're doing a L'Hopital, we're trying to find the answer. Well, this time it says, we'll give you the answer. Now you got to tell us about the function that got us to that answer. So it started turning things around. Good times, good times. This should be fun. All right, well, let's think about what we can do. Well, oftentimes the first thing we do is we say, well, let's see what's happening to this limit. So we know that our limit as x approaches 2, and we have x f of x plus 4 divided by x minus 2 squared. Well, initially, when we plug in 2 minus 2 squared is 0. All right, upstairs we get 2 times f of 2 plus 4. So if we just saw the limit and didn't know that the answer was 3, we'd say, well, this is what's happening to the expression. It's approaching 2 times f of 2 plus 4. Now, is this enough for us to figure it out, what anything should be? And the answer is yes, because, see, we have a nice piece of information. We know that the limit is 3, but more importantly at this point, we know there's a limit. So how does that help us? Well, it helps us because we have the following. You see this part right here. If this was not 0, then there'd be no limit, because when we have a non-zero number over 0, what it means is you have a number divided by a really tiny number, which means it's blowing up, it's getting huge. So there's no limit. So if it does equal 0, it's a maybe there's a limit. We can't say for sure, but as a general rule of thumb, if I have something downstairs which is 0, if the top is non-zero, definitely there's no limit, or the limit is infinity or minus infinity, depending on context. Since we know the limit is 3, then it says, well, the top can't be 0. So our conclusion we can draw at this point is we say, aha, that tells us that 2 times f of 2 plus 4 must equal 0. Or we could say f of 2 would be what? Move the 4 across, divide by 2, negative 4 halves, which is another way of saying negative 2. All right, so now we figured out what f of 2 is. Okay, well, now we say, aha, look, it's going to 0 over 0, which means what? Which means we can apply L'Hopital. So we apply L'Hopital. So this becomes our limit as x approaches 2. So apply the derivative of the top. The nice thing is derivative of 4 is 0, so that goes away. So derivative of the first is 1 times the second f of x plus the first x times the derivative of the second f prime of x all over the derivative downstairs. Okay, that's 2 times x minus 2 to the 1 times 1. So I'm doing the chain rule right now. All right, so what does that go to? Well, that's going to go to, notice when we plug in 2 here, we get 2 minus 2 is 0. So the downstairs is still 0. Uh-oh. Still have something over 0. So what's the upstairs? Well, it's f of 2 plus 2 f prime of 2. But now we go through the same discussion. We know the limit exists. So the top had better be equal to 0. Otherwise, there could not be a limit. So we can come to the conclusion that, f of 2 plus 2f prime of 2 has to equal 0. All right, so what does that tell us? Well, we know what f of 2 is, so minus 2 plus 2f prime of 2, there we go, equals 0, which really tells us that f prime of 2 has to equal 1. So now we know what f prime of 2 is. F prime of 2 is 1. All right, so what can we do next? Well, we can apply L'Hopital one more time. Say, look, this is the limit as x approaches 2. And downstairs, we'll get a 2, which means it's game over. Okay, whatever happens, it happens right now. All right, how about upstairs? Well, we're going to have f prime of x, then plus, do the product rule here. Root of the first is 1, so times f prime of x, so that's f prime of x, plus x f double prime of x. Well, that goes to, since we have a 2 downstairs, that'll just be a 2. F prime of 2 plus f prime of 2, so that's 2 f prime of 2. And then plus 2 times f double prime of 2. Now, what else do we know? We know what the limit is. The limit is 3. All right, well, now we're almost done. We do a little bit of cleaning up here. For example, we can cancel a bunch of 2's here. All the 2's cancel. And we know that f prime of 2 is 1. So what does that tell us? Well, it tells us that 1 plus f double prime of 2 equals 3, or f double prime of 2 is 2. And there we go. There we go. And that's our answer. Ah, beautiful. Beautiful. Mwah! I like these problems. They're a lot of fun. All right. One more problem for now. This is a great problem. And I won't say what the answer is at the beginning, but if you can see this and guess the answer, you're amazing. You're amazing. Well, we're not going to guess. We're going to work the problem. So, find the limit as x goes to 0 of secant x to the 1 over x squared. All right, what can we do? Well, first off, what's happening? Well, we have secant of 0. That's 1. So this is going to 1. Then we have 1 over x squared. Well, x is a very tiny number, so 1 over a very tiny number is a big number. So that's like infinity. All right, so 1 to the infinity. Okay, so what happens to that? Well, let's work on it and see what we can get. So, first off, can we apply L'Hopital? And why not? Well, no, we can't apply L'Hopital because the problem is it's not a fraction. You see, it's something to a power. And both pieces are like changing with x, but we don't need something to a power, we need a fraction. So, our first thing we have to do is convert. Somehow rewrite it so it will be a fraction. Now, the way we do that is we have to find a way to bring the power down in front. So, how do you do that? And the answer is you use logarithms. Okay, so what we're going to do is we're going to momentarily say, well, we're looking for the limit. Well, let's call this value L. So that's going to be whatever the answer is. X goes to 0 of secant of x to the 1 over x squared. Now, take the log of L. And here's the nice thing about logs and limits. Logs are continuous functions. Now, whenever you have a continuous function, if I'm taking a limit of a continuous function of stuff, I can move the limit inside. So here I have a limit of a log, so I can swap. And therefore, if I take, well, really I should say a log of a limit becomes a limit of the log. So I can swap the roles. So this is really the same as the limit as x goes to 0 of the log of secant of x to the 1 over x squared. Okay, good, good. Now, because we have log, the 1 over x squared comes down. So this 1 over x squared, down it comes. So this is our limit as x goes to 0 of log of secant of x times 1 over x squared. But really, we're going to write that as limit as x goes to 0 of log of secant of x over x squared, because our goal is to get a fraction. And now we have one. Okay, now, do we apply L'Hopital? Well, wait. Before we apply L'Hopital, what do you need? Check. Is it 0 over 0 or infinity over infinity? So, let's see what this does. Secant of 0 is 1. Log of 1 is 0. So this is going to 0. Downstairs, 0 squared is 0. So it's going to 0 over 0. So, good. It is going to 0 over 0, which means we can apply L'Hopital. All right. So we apply L'Hopital. Ah, L'Hopital, mon ami. Oh. All right. Still have our limit. Hasn't gone away yet. Derivative of the x squared. That's easier. We'll do that one first. 2x. The derivative of natural log of secant. Well, we'll do the chain rule. Whenever you're taking the derivative of a natural log of something, it's 1 over that something. So 1 over secant times the derivative of that something, which is secant times tangent. Now the secants cancel, so that's good. So it's tangent of x over 2x. All right, so let's just rewrite that, clean it up a little bit. So tangent of x over 2x. Well, what does that go to? It goes to 0 over 0. Tangent of 0 is 0, and 2 times 0 is 0. So what do we do? Well, we apply L'Hopital, right? Of course we do. Ah, L'Hopital. L'Hopital, mon ami. Okay, so this becomes the limit as x goes to 0. Oh, mark that we're doing L'Hopital, so we remember. Derivative of tangent is secant squared. And the derivative of 2 times x is 2. And now we're like, game over. Good, right? Because whatever we get, that's got to be our answer. Because there's nothing happening downstairs. It's going to be a 2 in the denominator. Well, secant of 0 is 1. So it's a half. And you're like, I never thought the answer was going to be a half. But is it a half? Be careful. Are we done? And why not? 1/2 is not our answer. And you're probably thinking, but we worked so hard. Why is it not our answer? Follow it back. See, follow the equal signs back, and that's not the answer, it's the log of our answer. So we can say that the log of our limit that we're after is a half. So if we want just our limit, our answer that we were after, we got to get rid of the log, which means we're going to take e to the both sides. E to the log of L is L, so you get e to the 1/2, or the square root of e. And I'll tell you, I would not have thought there would have been a square root of e as the answer. But we didn't have to guess. We had our friend, our tool, L'Hopital, to help us through. These are fun problems, and I hope you're having fun doing them. All right, well, thanks for joining me, my friends. Take care.